Sorry, I'm having a little problems here. Sorry about this. Okay. Having a little bit of problems with my iPad here. Apologize. All right, so
okay, so
yeah,
sorry, we can start. Okay, so
yeah, sorry.
So we can start the recording. Okay. All right. Welcome back, everybody, and we are now ready to start the last lecture by Ira. Please.
Okay. So let's briefly review what we talked about last time. So we're applying the effective field theory techniques to GR. And so this effective field theory, I should say, is called NRGR, which stands for non-relativistic general relativity. And what we did last time was we introduced, so we said our action originally at the starting point, so the point particle action, was some action which is a function of x dot, h, the potential, and h radiation. I think in the notes I used bar here. And we said the first stage of the calculation is to integrate out the potential mode, which left us to a sum effective, which is a function now only of h and r, of x dot, x and hr, where now the dependence on the x's has a kinetic piece plus a potential piece, where the potentials are is g m1 m2 over r plus v eih, which we calculated. So this is the 1pn correction. And we're left over with there's going to be some coupling of h. So hr is going to couple to x and x dot in some way, and that's going to allow us to eventually calculate the power loss. sorry. So does anyone use Notability? I'm having a little issue with my Notability here. The app Notability, anyone use that? No? Okay.
No.
All right.
No.
Well, I'll have to do my best given what's going on. Okay, so so the next thing we're going to do is we're going to calculate the power loss. And if you remember how we did that in electrodynamics, we matched on to a theory where there was a P dot E, and this P was sum over EI XI. So this was our L effective, right? Plus the kinetic pieces and the potential pieces for the constituents, right? And this guy was the total dipole moment of the system. And then we calculated the power loss by calculating the imaginary part of this diagram. And now we want to do something similar for the GR case, but now it's going to be slightly different because we know in general relativity the first radiation, there's no dipole radiation in general relativity, and that's because the dipole moment of a system is the total momentum, which is in gravity, the dipole moment is the momentum of the system, and the momentum is conserved, so it can't radiate. So just like charge didn't radiate in electrodynamics, momentum doesn't radiate, and neither does mass. So there's no monopole moment in GR. No, sorry, the monopole moment doesn't radiate in GR, and the dipole moment doesn't radiate in GR because they couple to conserve quantities, one being the mass, one the momentum. So the first thing that radiates in GR is the quadrupole moment. So the analog we're going to try to match to is the coupling of the quadrupole moment to the radiation field, okay? And then we're going to calculate an analogous diagram here to calculate the power loss. And we're going to do all this in a systematic way within the multiple expansion. Okay. Okay, so, but before we do that, we need to talk a little bit more to build up the necessary machinery about the finite size effects, because it'll teach us something about what we should do with radiation. Okay, so we said that taking a step back now, when we match onto a point, so we start off with a full theory with some extended objects, and we match the 2-point particles. That was our first step, right? And then we know the action for the point particles is minus mi. Right? And now we want to include finite size effects. Okay? So include finite size effects. So how do we do that? Well, we write down every term possible that's consistent with the symmetries, right? So all terms consistent with symmetry. And we do so in a polynomial in the fields, right? So higher, we know based on dimensional analysis that the higher dimension the fields are going to be suppressed by powers of the radius of the object, right? So when we make this logical step in going from here to here, we're automatically going to do so in an approximation based on this expansion parameter, okay? So what we want to do is write down all possible terms that are consistent with the symmetries at lowest dimension. Okay, and then if we want to calculate corrections in this expansion parameter, big R over little r, then we'll include higher dimensional terms as well. Okay, so our symmetries in this case are diffeomorphism variance, and again, reparameterization and variance of the world line. Okay. So to make this reparameterization invariant, I'm going to have to put in factors of square root of v squared here. And excuse me. Because this guy goes upstairs. And then there's going to be v squared downstairs. Sorry. And then the square root. Okay. Okay, so the first two terms that we can write that are consistent with diffeomorphism invariance and RPI look like this. They're linear, excuse me, they're linear in the curvature. So R here is the curvature, not to be confused with this R here. So this R is the curvature, the scalar curvature. Okay. But we immediately notice that we can drop these terms because if you remember from our last lecture, we said that we're allowed to use the equations of motion in the action. And Einstein's equations, sorry, there's a factor of a half here, is r mu nu minus g mu nu r over 2 is t mu nu. Okay, so if we trace this thing, if we contract it with the g mu nu, we find that r is proportional to the trace of t. And in vacuum, therefore, r is 0 and r mu nu are 0 as a consequence. So this is called the vacuum Einstein equations. Okay. Now, there's something a little bit funny here because, well, r mu nu isn't really 0 because the world lines carry stress energy, right? So, so am I really allowed to set it to 0? And so there's a bit of a mathematical subtlety here, which I don't want to gloss over. But so let's just talk about this for a little bit. So the stress energy we know is confined to the world line, right? So we've taken the stress energy, which had some finite volume support, and we've contracted it to the world line. So the stress energy will necessarily be proportional to delta, where x is sitting on the world lines, I should say. And so now if we look at this term and we rewrite it as in terms of the world line, so I've done nothing here, but I could do this d4x integral and return to this result here. Now, if I insert the Einstein equation here, this gives me another delta function. So this term is going to be proportional of delta of 0. So in general, in physics, the only sensible thing to do with delta of 0 is set it to 0. Okay, and this may seem mathematically floppy, but as we physicists tend to be. But physically, we know this has to be the right answer. And the reason is because we know Birkhoff's theorem. I'm not sure if I'm spelling Birkhoff right. Sorry if I don't. Which tells us that for the Schwarzschild solution, a spherically symmetric solution to Einstein's equations, there's only one free parameter. Which is the mass. And if these terms were to exist in the action, they would introduce two new free parameters, right? Because notice that this action is linear, has a piece which is linear in in the metric. So as a consequence of that, if I wanted to calculate the value of h mu nu at some point x away from the world line, well, that's just the same thing as particle physicists, we would say that's like calculating the one-point function. And so we would have our Feynman rules, are all the linear terms in the action would generate a field. And we know there's a mass contribution. And in fact, we know from Birkhoff's theorem, this can be the only contribution to the one-point function. Now, if we had this R operator, it would also contribute to the one-point function with a C here. Okay? And we know that's not allowed because we know from Birkhoff's theorem that the mass completely determines the value of the field at any point away from the source. So we can conclude, therefore, that our mathematical sloppiness is justified by our physical reasoning, and it becomes inescapable that that must be set to 0. Now, it's interesting to ask, last time I said that that setting the terms in the action to 0 is justified by use of the equation, the use of a field redefinition, right? So if you remember last time, we gave the example, if we have an action for a scalar field, and then we had some term that vanished by the equation of motion, then I could redefine and then plugging this back in cancels this term, but adds an order c squared term. So as an interesting exercise, you can check that the field redefinition of the metric you need in order to get rid of this R term looks something like this. So G goes to G plus this term that's a delta function. And you can sort of see why this is going to work, because once you plug this guy, I guess there should be a minus sign, and there should be a C here. I think I called this coefficient CR. That once I plug this into root GR d4x, this delta function here is going to collapse this piece onto the world line and exactly give you a minus C v mu v nu r mu nu. You have to differentiate it to see it, but you can do that as an exercise for yourself and see that that indeed is what works. So, and you can find a similar field redefinition that gets rid of this piece here. Something really wrong. I apologize. There's something really wrong with my iPad. Okay. So, as an interesting side note to this point, so therefore we can conclude that if I included this term in the action, or this term in the action, has no physical consequences. Okay. So this is really interesting because it teaches us something, gives us some insight into higher orders in perturbation theory. So I think I may have mentioned that I got into this business because there was this issue of strange divergences in these PN calculations that were a slight mystery at the time. And now I can explain to you what happened, how that mystery comes about, and how it's solved by working in the effective field theory. Okay, so we were talking about calculating potentials, and we said last time, well, you know, at 1 PN, we calculated this. And if I go to higher orders, there are nonlinearities. And if you go to 3 PN, so if you remember NPN, just to remind you, goes like V to the 2N. So if you go to 3 PN, which is V to the 6, you end up with diagrams that look like this. and similar diagrams that look like this. And if you calculate these diagrams, you'll find that they're actually log divergent. Okay, and that's so the potential should clearly be finite. So these are actually ultraviolet divergences. So if I calculated using dimensional regularization, I would find some 1 over epsilon pole when I calculate this diagram. Physically, where does this come from? Again, this is a classical diagram. There's no quantum mechanics here. So as I mentioned last time, a better way to draw it would be like this, with insertions of sources. That's a tree level diagram. So why does that, how can that possibly diverge? And the answer is that when you integrate in, if we're doing this diagram in position space, I would integrate over the position of this vertex in position space. And when I do that integral, in some region, it's going to overlap with these world lines, right? But these world lines are singular. So this introduces a UV divergence into the problem. Okay, so how do we handle a UV divergence? Well, as particle physicists, we're quite familiar with handling UV divergences. UV divergences are a consequence of ignorance of the correct short distance physics, right? When you learn about renormalization, it sometimes is a bit mysterious because, you know, you have these counter terms and there's all this technical mumbo jumbo, but it's really quite simple about what's going on, right? When you have an effective theory, it's only valid to a certain scale. And now we're doing an integral over all distance scales. So why should we possibly trust our integrals, the results for the integrals? And the answer is you shouldn't, right? And that's why you get the divergences. But because physics is local, that actions are local, and maybe if people have questions, we can discuss this during the Q&A afterwards, because this is a really important point. You're always assured that the divergences will look like local terms in the action. In the old days, that was called renormalizability. So that's telling us that somehow this divergence has to be absorbable into a term in the action. But what term is it? Is it the mass? Is it the mass is the only counter term we have in the point particle action. And so we can sort of figure it out by realizing, well, if the divergence is coming when this guy's sitting on this line, right? These lines here are all carrying very large momentum, very short wavelength, so I can contract them to a point. And all the UV divergence is sitting here. Okay? So that means that there should be some local term in the action for which we can absorb those divergences. Okay? Now, it turns out that if you calculate the Feynman rules for R, they will exactly reproduce this diagram, the divergent part of this diagram. Okay? So what that's telling you is that you can absorb the 1 over epsilon into CR. Okay? So that tells us everything we need to know, because we know CR is unphysical. So when we calculate this diagram, we can be assured that this UV divergence is unphysical, and I can just drop it. Another way of saying that is I can absorb the UV divergence into CR and then just do a field redefinition to get rid of it. Okay? So any UV divergence that occurs from a diagram like this that shows up at 3pn is unphysical and just can be tossed out. And I think that really demonstrates the power of this effective field theory formalism. By working at the level of the action, you allow yourself to renormalize the theory. Okay. Are there any questions about that? No? Okay. So let's move on. So if I can get, we're in the context again of finite size effects. If I can get rid of these guys, well, what's the first? What are the first finite size operators I can write down? Well, I can get rid of those guys, but I can't get rid of r mu nu rho sigma because that's the Riemann tensor, and Einstein's equation does not tell us it vanishes. However, there's nothing I can write down to contract with. So I could try to contract with V, but the symmetries of R are gonna make those zero. Anti-symmetries under interchanges of the coefficients. So there's nothing we can write down that's linear in R, and that's consistent with Birkhoff's theorem, right? If we had any operator which was linear in R, it would change the one-point function, and we know the one-point function is uniquely fixed by the mass. So we can write things which are quadratic in R. And so we can write things which go like r mu nu rho sigma, r mu nu, and then r lambda alpha beta gamma with some contractions, contracting them in various ways. But there's a much simpler way to do things. And let me show you how. So the Weil tensor is defined in this way. So you can decompose the Riemann tensor into a piece, into the Riemann tensor, and you could, depending on how you look at it, you can decompose the Riemann tensor in terms of the Weil tensor and the Ricci tensor and the scalar curvature. And and the reason we want to do this, so this you can always perform this decomposition. This is called the Weil tensor, and I'll explain to you the physical meaning of the Weil tensor in a second. It contains all the on-shell information of the Riemann tensor. So we can so this is the Weil tensor. And we can further decompose the Weil tensor into electric and magnetic parts. So given V mu, which is any time-like vector, in our case, we're going to take the tangent vector to the world line. We can decompose it into what's known as the electric and magnetic pieces of the Weil tensor. Okay, so these have the property that V dot E and V dot B are equal to 0, and they also have the property that they're symmetric and trace-free. Okay. So now notice why do we want to talk about the Weil tensor? Because if we look at R, then we know that on shell R and C are exactly the same because these guys are 0 by Einstein's equations on shell. So we've eliminated all this redundant information about the Riemann tensor by using the on-shell condition. And we're allowed to use the on-shell condition because of our ability to use the equations of motion. It's a redundancy. So E and B are analogs of the electric and magnetic fields in electrodynamics. And so E here is a vector and B is a pseudovector. So they transform opposite under parity. So parity is going to be one of my good symmetries. So the only thing I can write down looks like that. Okay, so those are the first finite size corrections. And these are exactly the love numbers, the electric and magnetic love numbers. And they're equal to 0 for black holes, as I mentioned in the first lecture. How do you know they're 0? You perform the matching, exactly the same matching calculation we did in the charged sphere. You put the system in a background field. You put the black hole in a quadrupole field, and then you measure the response, so delta Q. right? And delta Q in an analog to what we did before. The change in the so we're going to write back here. We're going to write H equals H background plus delta H. And then we're going to solve Einstein's equations in this background and read off delta H. And delta H allows us to calculate, just like we did last time, to calculate the change in the quadrupole moment. Last time we did the change in the dipole moment. And that allows us an exact analog to what we did last time to read off the CE and the CB. And these calculations were done in the past, there's few years, and they found that CE and CB are 0. Okay, so physically, what are E and B? And just to give you more intuition about why these things are the love numbers. So if you take the Newtonian limit of E, it looks something like di dj h00. Remember, h00 you can think of in the Newtonian limit as the Newtonian potential. So di h00 is the force, Newtonian force. And if we look at two charged particles in a background field, not charged, sorry, two massive particles in a background field, and there's some source here, some planet, and we look at, this is x1 and x2, and we want to calculate the tidal acceleration. So this would be the acceleration at x plus r minus the acceleration at x. This will be equal to exactly ri eij, because eij is this. So remember, so A is going to go like dh00. And now if I expand this guy, this goes like dA, but dA is going to be ddh00. Okay? So you can see that eij gives you the tidal acceleration. So now we can understand why this is the tidal, this is the polarizability. It's how things get pulled apart when you put them in a background field.
We have a question.
Yeah.
Yeah, hi. I have a question about this wild tensor. So if I think of this tensor as the part of the Riemann tensor which contains the on-shell information, so is there an analog to the tensor in Maxwell?
What would be the analog? The thing, the difference between Maxwell, so the Weil tensor. No, I don't think so. I don't think that, because, yeah, electrodynamics is conformally invariant, and the Weil tensor tells you how things transform under conformal transformations. So yeah, so I think not, because in electrodynamics you can always decompose F mu nu in terms of E and B directly without dropping anything, right?
Right.
Whereas here, R mu nu rho sigma is written in terms of C plus other stuff, which vanishes on shell. So the analog would be F mu nu is equal to a piece that goes like E and a piece that goes like B, plus stuff that vanishes by Maxwell's equations, right? But you can directly write F mu nu directly in terms of E and B without anything else. So.
Okay, thank you.
Okay, so these are our leading order finite size effects. My iPad is going crazy. so how do they scale in the post-Newtonian expansion? Okay, so let's look at CE, for instance. Okay, so on dimensional grounds, if we look at this term here, then let's do some dimensional analysis. Okay, and we know this has to have units of 0, and E goes like 2 derivatives acting on H, where now we still have 1 over m Plancks, because remember, R is a nonlinear function of H's. So to have consistent units for E, it should have units of 2, given that H always comes with a factor of 1 over m Planck. So this guy's going to have units of 4 in mass dimensions. This is going to have units of -1. So that must mean that CE goes like 3, has mass dimensions of 3, and therefore CE has to scale as the radius of the object cubed, right? Sorry, CE is -3, not 3. So CE must scale as R, and for a black hole, the radius is a Schwarzschild radius, CE cubed. So we might think that we were done at this point. However, in gravity, we still have a dimensional coupling around, which is m Planck. So we can always multiply that RS cubed by RS times m Planck to the n, some arbitrary power, right? And so we can't quite read off the scaling yet because we don't know what this n is. However, we can fix n by consistency because we know that the potential that is generated by this E squared, so here's an insertion of the E squared operator here. It starts off with 2 gravitons, so the first Feynman rule has to have 2 gravitons coming off of it. And we put 2 mass insertions here. Each one we determined last time scales as root L. Therefore, and we know the potential should scale as L. So therefore, this guy has to scale like L to the 0. Okay. So if we use all the scaling rules we introduced last time, then this term scales as L to the n over 2 minus 1, v to the r plus n over 2. Okay? And since it has to scale as L to the 0, it immediately tells us that the only consistent answer is n equals 2. But at the same time, not only do we learn how it scales with n, we learn that it scales with v in this way. So this is 5pn. This is sometimes called the effacement theorem. This was first pointed out by Thibaut Damour some years ago, using very different arguments, using physical arguments. Here, we use no physics at all. We just use, well, we use basic effective field theory, but we didn't have to understand anything about GR really to determine this scaling. It just came out of the fact that every term in the action scales homogeneously, allowed us to extract that. So this is the reason I mentioned in the first lecture that 5pn is really the ultimate goal of all the people working on analytic calculations in gravitational waves. So 5pn is the goal because if you want to extract the tidal information, so these CEs contain, well, first of all, there's this remarkable prediction that black holes are really fundamental objects. They're point particles in the sense that you can't distort them. So they really are almost like fundamental particles. Or in the case of a neutron star, the CEs would encapsulate all information about the equation of state, whether on its quarks or hadrons that are in the high density QCD region. But if you want to be able to extract it from the data, then you need to know the background at 5pn. So it's just like we do at the LHC. If we're looking for new physics, there's always going to be background. We have to calculate the background to the order of accuracy that we need to extract the new physics. In other words, the data has a piece which goes like CE in it, which is 5pn. And then there's other 5pn stuff that's not CE, that's coming just from, say, the 5pn correction to the Newtonian potential, things like that. So there's a huge amount of work to be done because we need to calculate these in order to extract this from the data. Now, for the case of, I should say, for the case of neutron stars, it's reasonable to believe that even though it scales as v to the 10th, it will be enhanced because the radius of a neutron star can be larger than the Schwarzschild radius. So it gets enhanced numerically, people believe, by, say, a factor of 10. So for a neutron star, you might hope that at least numerically would scale as, say, 3pn or 4pn, somewhere in between. So our chances of measuring CE for a neutron star are pretty good, I think, in the not too distant future, and eventually we will be able to extract the Love number from black holes and test this prediction of GR. Okay, so this is a natural stopping point. We're at 8:43, so why don't I stop for questions here, and then we'll take a break.
All right. If there is any question. Don't see any. Oh, one. Max?
Yes, I have a question about basically the applicability of this effective field theory formalism. So far we have done everything on a classical level, right? So, but there are also people, I think, who try to, or who write down models like that around black holes. There are maybe some scalar fields or things like that. So, so if we want to also incorporate to this classical GGR case also some quantum fields. So, can this readily be done in this formalism, or is it much more complicated?
So it sort of depends on what you want to do. So before we talk about the quantum issue, we could ask, how would we, for instance, how would we include, say you wanted to add scalars to GR, right? That's not a problem. So that's the beauty of the effective field theory formalism is that you can add things as long as you do things consistently. So for instance, if we had a scalar field around, then I could add this to the world line, and that would be consistent with the symmetries. Unless, of course, say, usually there's a discrete symmetry and their phi goes to minus phi. So I would add, say, something like that, okay? Then I can just turn the crank and do everything I did before. So now there'll be, for instance, corrections to the potential, right? Because depending on how it couples, say it only coupled in this way, then you would have, let's see. So let's come up with some terminology, with some notation. So this is going to be our graviton, and we'll make the straight line the scalar. So that means that the scalar would has two guys coming off of here, and then one graviton, right? And that would change the potential between the objects, right? Mm-hmm. And similarly, when we get to radiation, you can include the phi fields as well. Now, in terms of quantum, I think that, if you power count the way we did, there's really no way ever to get a quantum effect that's not down by h bar over L. And you'll see tons of papers where people where people make claims about seeing quantum, and the only way to do that is to put in some huge number into the theory that somehow multiplies the quantum corrections and compensates for this tiny number, right? And I don't know of any reasonable way to do that and make it work.
So, but regarding this, so this h bar of L, so is there a difference of if I try to if I try to think of GR as a quantum theory and incorporate quantum effects of GR, or if I really treat GR completely classical, but try to incorporate quantum effects of, for instance, this scalar field here, or would those effects also exactly scale?
Those effects will also be down, yeah. So certainly, so you could consider. So for instance, here's a quantum effect that's kind of trivial that you could include. So for instance, suppose that the scalar field was self-interacting, right? So if the scalar field was self-interacting, it could have some quantum corrections to their lines, right? But that's not gonna really do anything but just sort of change the values of the couplings of the scalars to the lines. And you didn't know those anyway. So you wouldn't be able to tell if it was a quantum effect or not. It just renormalizes the classical couplings in some way. So yeah, I'm not optimistic about ever seeing any quantum effects in these systems.
Okay, thank you.
Okay, next is Prisco.
Yeah, I wanted to see if my intuition for what happened at first order in finite size was correct. So basically, we started from point particles. Then we went to first order, which was basically spherical particles. And then Birkhoff theorem tells us in GR, spherical particles act as a Schwarzschild. So they're basically point particle again. So there is no correction to the zeroth order.
Yep.
Is that what's happening physically?
That's correct.
Okay.
Yep.
Great, thanks.
And next is Arman.
Yes, hello. So regarding this last thing that you mentioned, okay, maybe you'll tell something in the continuation of the lectures. Now that you mentioned the background and you drew this analogy with the LHC. So, for example, here in these theories, how can you, or better say, what can you use as your data in order to, I don't know, constrain any of those Wilson coefficients, or I mean, can you do it like in this, let's say, LHC way, in sense like what mostly phenomenologists do, or?
Yeah. So the process by which you try to measure these coefficients is very different than it is at the LHC, although in essence it's the same. So I mean, so what does the data look like? Well, the data looks like it's you calculate. I don't know if Valerie discussed the LIGO detector. So you have a laser going this way and a laser going this way. And when the gravitational wave passes through, there's the relative time it takes for each beam to go back and forth changes, because these distances fluctuate as these distances fluctuate. And so what you see is basically you're measuring the distance between the mirrors.
Mm-hmm.
So if you plot it, it looks something like something like that, right? And so the shape of this waveform is going to be sensitive to CE.
Mm-hmm. Mm-hmm.
And So what they do is they come up with these templates, which I think I mentioned in the first lecture, where you consider some waveform, let's call it WF, is going to be a function of M1, M2, and let's say C1 and C2. Okay?
Mhm.
And this is going to be some complicated function that looks something like this. And then they scan this parameter space and try to match onto the data, right? So they
Okay.
project it on and they see how good of the fit is, right?
Mhm.
And so actually, so what you do, they do something called match filtering, which is something from engineering where you basically, you convolve the data with the prediction, right? And you see how large this thing is, right? That's like the overlap of the two.
Okay, okay.
And so this is, as you might imagine, this is a very tricky business with very sophisticated methodologies for errors and so forth and so on. And the CE is remember, v to the fifth is typically like 10 to the minus 4 effect, right? So you're looking for a 10 to the minus 4 effect that differentiates different waveforms. So it's quite a challenge. Of course, one thing I learned being around for a while is, since I was around before the LHC started, is there were a lot of things that we as theorists thought, oh, they'll never measure that, right? And experimentalists are always under representing what they can actually do. So never underestimate experimentalists. It's amazing the things. If I could go back and say, oh, they'll never measure that, so don't bother. There are tons of things where all of a sudden they're measuring things we could have never imagined they were measured. So even though these things seem impossible, given enough time, it will get done. So as theorists, you have to decide for yourself: am I willing to work, to sweat for 2 years to make a prediction that's not going to be measured for 20 years, right? And that's something you have to decide for yourself. As a young person, that's particularly hard to do, right? So you want to make a prediction for something that's to be measured very soon, but there just aren't too many things like that, because there are other people 20 years ago who have made those predictions already, right? So
Okay.
Right. I don't see any more questions for now, so we can take a break, small break, and we convene in 5 minutes.
okay. Thanks.
Hey, Ira. Whenever you are ready.
Okay. So let's move on now and calculate the next logical step, which is to discuss radiation. So as we said, so now again, we've gone from the point particle, we've integrated out the potentials, and all we have left is some action, which is a function of x dot, and h bar, which is h bar is the radiation field. So this part includes, the kinetic piece plus the potentials, which we calculated, including the IIH, for instance. And now we want to calculate the coupling to the radiation field. And we do so by, again, utilizing symmetries. So it should be diffeomorphism invariant. And so we should write down everything we possibly can that's diff invariant, right? So we know what the form of the action is going to be. It's going to have every possible coupling to E and B, right? Because now we're using E and B because we know that when we use the equation of motion, we could trade R for E. Okay, so we can write down terms like this, for instance. So now notice, of course, the system will contain terms which are linear in the metric, because it's no longer a point particle. Now we're talking about the entire system, right? So there's no Birkhoff's theorem or anything like that, because now the entire system is obviously not just the Schwarzschild solution. So we can write down terms that look like this, and then we can write down a term that couples to B. The 4/3 here is convention. And then we can take derivatives of B and couple to them derivatives of E and higher dimensional operators, which will be suppressed in the post-Newtonian expansion. So here I just wrote down the first couple. So at this point, we don't know what this is. So this is called the mass quadrupole. And this is sometimes called the current quadrupole. And so one of them is even parity, and the other one is odd, right? Because E and B are even and odd. And then we could write down higher terms as well. At this point, Q and J are functions of X and X dot, Xi and X dot I. Okay, and we don't know what those functions are. And our job is to figure out what they are. In terms, we're fixing these F's, that's called the matching procedure. So you can think of Q and J as Wilson coefficients for those of you who have more experience with effective field theories. They depend on the short distance quantities, which are the point particles' positions themselves, okay? Now, notice we could also add terms that look like this, even though they do not look diff invariant, because they actually are. So remember how H transforms under a diffeomorphism, under a general coordinate transformation, where X is going to X plus C. So choosing T as our affine parameter, we can see that H00 is going to go to H00 right? So delta S will be M times C0 dot. Now, this is a total derivative, so I can set it to 0. And the reason is because dm dt is 0. So this is, again, a manifestation of the fact that it doesn't, the mass doesn't radiate, right? It's constant. It's a conserved quantity. This H00 will never lead to any real radiation. And the same thing goes for here, where H0I couples to the conserved quantity Pi, the momentum. And if I go to the center of mass frame, in fact, I can even set that to 0. That's the net momentum of the system. Okay? So those are all the possible things that I could write down. And now the next question is, the job of a theorist is to calculate the Wilson coefficients. Okay? So how do we do that? So we do that through our matching procedure. And actually, there's a trick to doing this. So we know that in general, the coupling of the metric to the action can always be written in this way, to the matter action. This is the definition of T mu nu. Okay? Which I think is 1 over root G. So this is true by definition. So this equality should really be an equivalence. That's the definition of T. Okay? So we can concentrate on if we're interested in the radiation, Hij contains the radiation. In the sense that, remember, gravitons are transverse, traceless excitations of the metric, okay? So if we're interested in matching the real radiation that's coming from these terms, we can shortcut the process by focusing just on the physical polarizations and then extracting what these Q's are and utilizing the covariance of the result to extract Q mu nu. Okay? So just as in the case of electromagnetism, we multipole expand the field in to be consistent with our homogeneous nature of our power counting. So we're going to write S as -1 over 2m flank. Okay, so we're just following our noses from what we did before. Now, to gain a little intuition as to what's what in what order in perturbation theory in post-Newtonian expansion, we can use the fact that T00 will start as v to the 0, T0i will start as v to the I, and Tij will start as vi vj. And how do we know that? Well, physically we can tell because this is going to start with a mass, this is going to start with the momentum, and this guy, since it has two indices, it has to be vi vj. It could be a delta ij piece there too, but there's no reason why there shouldn't be a vi vj piece. So this just, you can think of all, if you don't want to use any physics input, you can just, this is just covariance under rotations. Okay, so so now if we're interested in extracting things to order v squared, then remember that each derivative here is going to cost a v. And then we also have to keep track of which components of t we're including because of the different scalings. Okay, so you want to, if say we're only interested in calculating, let's consider v to the 0. Okay, so that's gonna pick out the T00 piece. Okay, so now I'm going to prove the following statement. I'm going to prove that Tij d3x is equal to d3x xi xj T00 double dot. Okay, so how am I going to prove this? I'm going to use the fact that d mu t mu nu is equal to 0. Sorry. Sorry, my phone was off, but not my computer. There we go. Apologize. So so d0 t00 plus di ti0 is equal to 0, and dj tj0 sorry, d0 t0j plus di tij is equal to 0, right? So I have T00 dot is equal to di ti0, and T0i dot is equal to di dj tji. And let me differentiate both of these guys. So now I have T00 double dot is di ti0 dot, which is di dj tij. So why is this useful? Okay, so now if I let me integrate this equation. So now I've got xi, xj, t double dot 0, 0. Actually, let me write it as AB. And now I can integrate by parts. Okay, so I have this relationship. This is called the moment relation. So why is it useful? So I've just proven this for you. Why is it useful? Because now if we focus on the physical modes, so the leading order piece in the multipole expansion is going to be Tij Hij0 d3x. But this we can write as x I xj t00 double dot h ij. Okay. So I can integrate this by parts. So this t00 sits on the world line. So this guy looks like okay, and d3x. Remember this x, these x's are not the world lines or this x. So when I integrate by parts, I can push this over to hij. Okay. So t00 scales as v to the 0. And so the question is, how does this match on to something that looks like q mu nu, e mu nu? Well, if we look at the linear piece of E, so Eij at linear order, looks like that. And so this coupling, we can look at, well, this is going to contribute to one of these terms, and we can pick out that contribution, which is just here. Okay, so the beauty of RPI is, the beauty of the symmetries of diffing variance is that all I need to do is pick out one piece, and I can get the coefficient, because I know there'll be other contributions, which I haven't written down here, that will automatically pick up these terms. Right? So there are other contributions at this order, say from these terms, that will fill that out, and that allows me to extract Q ij is being equal to d3x xi xj t00. Okay, that seems most of you know that that is just the formula for a quadrupole moment. So why didn't I bother just writing that down in the beginning? And the answer is because if I go to higher order in the PN expansion, the shape of this, the dependence of this gets much more complicated, and it starts involving more than just T00, because remember, T00 is order the V to the 0. So this is the V to the 0 contribution to the quadrupole moment. But if you go to higher orders, then this becomes a much more complicated function of both Ti0, Tij, and the x's. Okay, so So you can go to higher order in a systematic way just by including all the terms that you have here. And this tells you the form of the Qij in the post-Newtonian expansion. So Qij is going to have a piece that looks like what we have here. Plus higher order pieces that are functions of the T0I and Tij, so forth and so on. Okay. So you might be a little bit troubled, for those of you who've had a little bit of group theory, that this does not, so Qij should transform in an irreducible representation of the rotation group. And this certainly does not look like it's irreducible, because if you have a 1 cross 1, the 2 piece, so remember this is 2 plus 1 plus 0. The 2 piece should automatically be symmetric and traceless, symmetric and trace-free. Sometimes it's written like that. So this looks symmetric. It certainly doesn't look trace-free. So we would have expected xi, xj, minus 1/3 x squared delta ij. And in fact, if you actually included all the pieces, you would get this piece, but you don't really have to, because as I said, Eij is traceless. So Eij delta ij is 0. So you're free to just add that to the quadrupole moment and get an irreducible representation. So which is just a statement that on shell, this is effectively irreducible. Okay, so what we've reduced the problem to, so we've reduced the problem with our action now, going, working in the center of mass frame of the system. And we know these Qs are going to be basically moments of the T's, right? So our goal will then be to extract T. Once we have T, that'll give us Q. Okay? So how do we extract T? Well, we said that S defines T in this way. So if we can calculate the linear coupling to the potential to the radiation graviton, I think that was H bar, that will allow us to extract T. Okay? So if we're interested in, say, at the leading order, we want to extract T00, well, that's easy. We know from expanding out this term that there's going to be a term that goes like M d lambda H00. So at leading order, T00 is just going to be M. Actually, so I should take it back. Let me be more precise. Okay, so there's gonna, and then there's a MI here. So there's going to be, the leading order is going to give M1, H00, d lambda 1 and if we really want to pull out t, then we should really write this as d4x d lambda delta 4 x minus x1 and 1 h00. So let's call it I. Okay, so therefore t00 at leading order is just the coefficient of the linear term of h00. So that's going to be up to factors of m Planck. There should be a 2m Planck here. It's going to be d lambda sum, or sorry, sum over I okay, and that's your t.
Ira,
Yeah.
we don't see the last part you write, I think.
Is it not mirroring anymore? Can you see the screen at all, or is it just?
Yeah, we can see the screen until t not equal.
Huh. Stop mirroring. What about now?
Okay, now yes.
Okay. So this is the leading order T naught naught, right? And all it is the coupling to the masses of the particles. Now you could calculate the corrections to T naught naught. So in addition, for instance, we know that the radiation graviton couples to all sources of energy. So if you included this term in the effective action and this term and read it off, all that's going to do is change m to m plus v. So now h00 is going to couple to the total. Okay? Because the potential energy contributes to the coupling to h00. Okay, so you could go on and calculate pretty much anything you wanted in this way, higher orders in the multiple moments. And once we know the Q's, so in this case, the Q is, we just said Q ij. Then we could calculate the energy loss by taking the imaginary part of this diagram, where there's an insertion of Q here, and there's an insertion of Q here. And this will give you the power loss goes like 3 derivatives acting on quadrupole moment. This is the famous quadrupole power loss formula. Okay, and this comes from exactly the same calculation we did in the case of electrodynamics. And if you want higher order power losses, all you need to do is calculate higher orders in Q. And if you go to higher orders, you're going to have to include the power loss also due to the J's, to the current mass quadrupoles, and so forth and so on. Now, something interesting happens when you go to higher orders, because remember we said that there's coupling, H00 couples to the mass, and then it couples to Q dot E. And so now if I want to calculate to higher orders, I need to include terms that look like this. So this is a mass insertion, and it couples to H00. This is a potential graviton, but it's a potential that's generated by the sum of the two, because we've already integrated out all the potentials in between the particles. This is now the potential. We shrunk this to a point. This is now the Schwarzschild solution of the binary system itself. So this is basically a graviton scattering off the Schwarzschild solution before it reaches infinity. So I take the imaginary part, I cut this diagram as we would in a field theory. And this corresponds to, this is called the tail effect. And it's much like Coulomb scattering. And in fact, if you calculate this diagram, you'll find that there's a Coulomb divergence, just like there is in quantum mechanics, even though this is completely classical. But of course, the Coulomb divergence, just in quantum mechanics, should not contribute to anything physical. And in this case, it doesn't as well, because the Coulomb divergence actually gives an overall shift, an infinite shift to the phase. But since the phase is the phase at any given time isn't measurable, all you can calculate is changes in the phase. That divergence doesn't play any role physically in the calculation. Okay, so sadly, I've run out of time. I didn't expect to, but there are lots of other topics that we could have covered. The next topic that I was going to cover is how to include spin, which is interesting. And another fascinating is how to include absorption or tidal heating. And this involves very interesting field theory because heating comes from some internal degrees of freedom absorbing the energy. In the case of a black hole, the black hole will absorb the energy and grow in mass. And we can actually calculate how those effects change the signal. Those are particularly interesting, of course, for neutron stars, because again, that teaches us something about the internal dynamics of the neutron star. But I've run out of time. If we have time within the question session, I can say a little bit about spin, just to give you a little bit of a flavor of how spin works. But let's stop here and see if there are questions about the second half of the lecture.
All right. Thank you, Ira, very much. So now we can start directly the Q&A. So I just see a question from Max.